Hello class. Today we are going to be talking about the dissolution of covalent compounds. So how is it that covalent compounds dissolve and how is that different from ionic compounds? Before we go there though, let's quickly again talk about ionic compounds. So aqueous solutions are solutions in which water is the solvent, and we often call water the universal solvent because it can dissolve so many things with its strong polar interactions. However, with covalent compounds it gets a little bit more complex. Right? With ionic compounds it was easy. Right? Our solvent had to be polar. Why was it that oil could not dissolve water? Well, oil only has those weak interactions, right? London dispersion force is present. And that was not enough to overcome the strong electrostatic attraction between salt ions. However, when there is a polar solvent, the salt ions can then dissociate into their respective ions. They become solvated, right? They can be surrounded by water. At which point we say that they are now dissolved in solution. They are now in the aqueous phase, right? They are now in the aqueous phase. And we can say that they have dissociated because they are no longer in a compound, right? Those ions have split apart. Now when it comes to covalent compounds, we do not dissociate the compound. Right? It's not ions that are held together. What is a covalent compound again? Well, a covalent compound is not ionic bond, it's a covalent bond. It's a sharing of electrons between nonmetals. So when it comes to the solvation process of covalent compounds, things are quite different. Now, we do not use the word dissociation when we talk about molecular compounds like sugar, for example, because they do not separate into charged particles. When they dissolve as a whole unit, as a whole molecule. Now, we do still use the term aqueous, right? If I take sugar and I dissolve it in water, well, we're still going to say that that sugar is in the aqueous phase, right? It's dissolved in water. So here's an animation of these solutes being dissolved and solvated. Now the sugar particles are being surrounded by water, but unlike with our ions, it's not like, all of the water's oxygens are interacting with our sugar, or all of the water's slightly positive hydrogens are interacting with our sugar. What is sugar? Is it polar or nonpolar? Well, sugar is polar, right? It's going to have an area that is slightly positive and an area that is slightly negative. And you should already see where I'm going with this. This slightly negative area, well, that's going to be surrounded by those slightly positive hydrogens. And that slightly positive area of our sugar molecule is going to be surrounded by those slightly negative oxygens of water, right? So you still have electrostatic interactions between solvent and solute. It just looks a little different than with ionic compounds. So what is the rule? What is the key rule that you need to know? And that rule is like dissolves like, right? If you have a polar solvent, that will dissolve polar solutes. If you have a nonpolar solvent, that will dissolve nonpolar solutes. However, any mixture of polar and nonpolar, they will not dissolve, right? If you have a polar solvent, nonpolar solute won't dissolve. If you have a nonpolar solvent, polar solute also will not dissolve. So like dissolves like. You need to remember that. super important for determining if something will dissolve or not. So now we have to explore the different possible situations that can arise when we mix two substances together. Right? We have to look now at the molecular level at what's happening. So what is happening then when we get a polar solvent mixing with a polar solute? Why is it that it dissolves? Well, the solute-solute interactions are broken by the interaction of solute and solvent. And how is this happening? Well, the slightly positive part of the solute interacts with the slightly negative part of the solvent and vice versa. I'm going to draw a picture here. It's going to look very similar to the dissolving of our ionic compound, except again, there's no dissociation. Now, our sugar molecule here, we're going to say that part of it is slightly positive and part of it is slightly negative. I'm just drawing it like this for simplicity's sake. Now, our slightly positive part of our sugar, well, what's going to be attracted to that? What part of our water molecules? We're dissolving sugar in water right now. Well, our slightly negative oxygens are going to form electrostatic interactions with that positive part of our sugar. So, our oxygens of our water molecules, remember they are slightly negative, they are going to form interactions and solvate this part of our sugar. Now what about the slightly negative part of our sugar? Well, that's going to be those slightly positive hydrogens. So our water molecule now, right, our slightly positive hydrogens are going to be interacting with this negative component here. So it is this that solvates or surrounds our sugar molecules. So that's what dissolving our sugar will look like in water, right? A polar solute and a polar solvent. Now let's explore the next possible scenario. So what if instead of polar dissolving in polar, we have polar solvent and non-polar solute? What would happen in this case? Well, in this case, it would not dissolve. Right? It would not dissolve. Why is that? Well, the interactions between solvent molecules are much stronger than the solvent-solute interactions, therefore it does not dissolve. Because remember, a big part of dissolving is breaking the interactions between your solvent, breaking the interactions between your solute, and them forming now new interactions together. However, if your solute isn't really forming strong enough interactions with your solvent, well, your solvent molecules are just going to stay stuck together, right? So that's what's happening here. Our solvent molecules have very strong interactions, say like water, for example, those hydrogen bonds. If you throw something like wax or some nonpolar substance within the water, it's not going to dissolve, because the wax just has London dispersion forces that it can interact with water. So that is why polars and non-polar do not dissolve. What about the flip though? What about the flip side? What about if I had a non-polar solvent and a polar solute? Well, I'm sure you can guess already the situation. The interactions here between the solvent and solute are too weak to separate the solute molecules. This one's perhaps a little easier to understand, right? If I put sugar in oil, sugar in oil, the sugar has strong dipole-dipole interactions, whereas the oil just has those London dispersion forces. So the oil gives it a little tiny tug, right? Very weak IMFs. The sugar is just going to stay stuck together. So that is why nonpolar and polar do not work yet again. And then lastly, we have nonpolar solvents mixed with nonpolar solutes. And in this situation, it does dissolve. Remember, like dissolves like. Why? Well, the solute-solute interactions and the solvent-solvent interactions here are very weak. And as a result of that, there isn't these large forces that have to be overcome in order to separate them. So, the LDF then between solute and solvent will cause dissolution. So those LDFs between your solute and your solvent are going to be strong enough to separate that solute and solvate it and completely dissolve it. Right? So it's going to look very, very similar to the last drawing I just drew. The only difference is that London dispersion forces, right? Let's say that this here is our solute, for example. Right, here's our solute. And why did I draw it with positive, negative charge? A little bit of physical properties review. Well, what is LDF? LDF is caused by a temporary dipole, right? That shift in electron density. So this is our solute here. And remember that this is a temporary dipole. Right? These are LDFs. And our solvent here will have the same thing going on. Right? Our solvent has a temporary induced dipole. I probably should have said induced dipole, sounds a bit better, but that's fine. This is solvent. Right? And this is another just temporary dipole. And it is these LDFs that cause dissolution. Right? I can draw another solvent particle down here. Positive is attracted to the negative, and you get the idea. Right? So with nonpolar and nonpolar, these temporary dipoles, induced dipoles, they are very weak interactions, but since the forces holding together your solute and solvent are also extremely weak, it is enough to overcome those solute-solute and solvent-solvent interactions. So next class, we will be talking about the rate of solubility. So what affects how fast something will dissolve. Okay, well that's it for today. Have yourselves a lovely, lovely day. And let me know if you have any questions.